microphone.
Can you hear us online? Just give us a thumbs up if you can hear us online. And then let's just make this a view that's... Okay, perfect. I hear tons of thumbs up. I just want to get started so people that do arrive on time are not penalized for people that don't show up. This is the most important class. I often say this, I was thinking about coming back and I realized I should do this class a little bit earlier than I often do in the course of the class itself, because I think eventually this will be the starting point and the launch point for you all to be thinking about projects. You know, we all come in and join this class primarily to execute and do stuff. Are you recording?
Yes.
Okay. So I think, yeah, for folks, just as a general request, if you can, please turn your cameras on. It's kind of fun to see people. Please turn your mics off. It's useful if you are on campus to come join together. What we're going to do today is spend some time thinking about how to structure our projects. And also a framework that I often like to use in the class that I learned from one of my favorite, I would say, teacher in grad school, Alex Slocum. So we'll spend a little bit of time on that framework of just taking tough problems, breaking them down into pieces, and we will use a very specific methodology for it. And then there will be an assignment post this, where you will start working on the problems and projects that you're excited about, break them into this methodology. Before we start, how many of you have taken a design course before? Somewhat? Okay, so 2 people. Anybody online, if you've taken a design course, just raise your hand. There might be pieces of something like that you might have done in a design course. What's different is that this has to be extremely quantitative. So again, you know, the approach that we are trying to take here is keep our sets of design parameters that we'll talk about, but convert everything into numbers and analysis. So it becomes far more quantitative. So you can actually make good decisions. And I think one fun thing to do before we get started is to choose a few sets of problems that we could try running this methodology on. We'll just call this methodology FRDPARRC. And I don't know if you can all see the whiteboard. If I move to the whiteboard, okay, you can folks on the screen or online actually read what's written on the whiteboard? Somewhat, or when I stop blocking it? Can you all read the whiteboard or no? No?
Not focused.
Oh, I think they can still hear it, right? Oh. No. No, you should. Let's go back.
Keep this here. Okay. I think you can just try spotlighting it. Okay.
Yeah, can somebody on the online just mention, you should pin, yeah, just pin that one, spotlight for everyone. There you go. Okay, can you all read my screen or the whiteboard at all or no?
I think I can read the biggest one, but like not the one below it. And there's like a giant reflection.
Anybody has an eraser? We're still figuring out how to use this. Actually, that might have been a better board. You want to just roll that board out? It's shiny board, but not so easy. Okay, much better. Okay, so before we even begin, maybe let's just do a little bit of a kind of show of hands and interest. You know, I think I had talked a little bit about 3 or 4 broad problem areas. in education, in health. We discussed a little bit about malaria. We talked a little bit about in the context of education really early on. We talked a little bit on the context of climate. And of course, there is some threads that I've mentioned in the past on the environmental side. I'm just curious, which categories do people fall in as you're starting to think about ideas that you're passionate about? Some of the by the numbers problems that you guys have already thought about. Are there things or categories that jump out to you that you feel very strongly about? Is there a problem that you came in to tackle in this class already before you walked in? Does somebody have, I know, Yuji, when I was talking to her, she's very passionate about that problem in Congo, for example. Are there other problems that people are passionate about? Yeah. Can you also just say your name? Just so I'm gonna start remembering them now. Yeah.
Sorry, I'm FRDPARRC, biodiversity monitoring.
And then at what scale, is there a specific, we could be thinking about the ocean, we could be thinking about insects.
Really land-based, especially rainforest-based biodiversity.
Uh-huh.
I think insects are super interesting, but I think there's a lot of different problems that can be tackled.
And so kind of, I'm thinking about one specific, say, the Amazon rainforest, a very specific. And so I think we'll use an example to just see how do we design this FRDPARRC around something like other problems, ideas people are excited about. This doesn't have to be your project. I'm just curious, something that you have thought and something has bothered you. I mean, a lot of things bother us, and it's a little bit of making sure you're actually okay talking about them. Yeah. Anybody wants to go? There must be problems that you guys want to solve. Yes. Somebody online? Go ahead, Weber. I just want to hear a few problems that people are passionate about.
Yes, Professor. Actually,
Yeah, go ahead.
I live in around the Delhi region of India, which is the capital in the Delhi NCR. And the air around Delhi for about 4 or 5 months in the air stays in the hazardous level, which is primarily attributed to stubble burning in the adjoining states and the vehicles and fireworks at that time.
So air pollution in general, and I think one of the threads is that as you're thinking about that problem, you could also break it down into many other ways. One can be focused on places where the monitoring doesn't even exist. The other could really be much more about health implications and thinking about what happens in the context of people that experience it. Something else in the middle could be, how do you mitigate exposure of people that don't have a choice, have to be outside? And so eventually it's important, the process that we'll apply today, we'll try breaking down the broad ideas that you might have into something very concrete, and then just say, how do I tackle something like this? I'm going to take one more problem. So that's fantastic. Maybe let's take one more problem. Anybody who wants to? Niam, I don't think we've heard from you before. You want to go? Yeah.
I'm interested in microplastic pollution and ways of measuring it, but like globally scalable ways of measuring it, because everybody wants to reduce microplastic pollution, but we need to know how much is there in the first place. So something cheap and scalable to measure microplastics in the sea.
So now that's a very concrete problem, right? We all know it exists. And then the question really would be is where would we begin? And so I think I just want to use 3 of these examples, and then maybe one I'll mix in from a more historic reasons is something that all of you got a chance to see in Quill, right? On the, did anybody get to play with it? You guys make some blood smears?
Yeah, we tried with
Okay, so with real blood?
No.
Okay, come on. We could go to the lab and, I mean, some of you will potentially choose working on medical issues, so it is valuable. If anybody wants to get trained on handling blood, there is a path towards that. But that object that you saw came out of, a lot of this exact same process. So we'll just choose that also as an example. So blood smearing. And one of the things that I want to do just today is to get a sense for you guys with pencil and paper, and your teams will have a chance to just start thinking about most of these things. Okay, let me figure out where this is the farthest things. Okay. So the process that you'll use, and this will be kind of the first assignment that you will all do in this space, is we call this FRDPARRC, and I'll kind of describe the acronym. So this stands for functional requirements. We're going to try to really put numbers to what do we really care about. So if you care about biodiversity, you really have to ask, what is the functional requirement of a solution that I might care about? This might include cost, because if I had $1 billion and I needed to map a kilometer of an area, that would be a different type of a solution. So functional requirements essentially are the key things where you say that this is the question that I'm interested in. It's not the idea. It's not what you will actually implement. DP is design parameters. We're going to write down some of the design parameters for this, which this is really where ideas start to flow in. This is when you make whatever you're thinking about as a functional requirement very concrete. So if this is a little bit that, oh, it has to be a low-cost solution, here you must say that the number that I put in is $10 per square kilometer of mapping, for example, right? A stands for analysis. This is really how do you prove to yourself that this is even feasible, right? How do you know that you haven't broken a law of physics in coming up with a design parameter that, oh, you want it? That doesn't mean that you can have it. R is references, to just make sure that the people that are evaluating your FRDPARRC sheet, which we will be doing the same, we'll print these out so you guys have these big sheets that you can write on, and we'll do this as an exercise. These are references that give people kind of confidence in how you implemented that solution. Now this is risks. There is always unknowns in any design process. So there will be lots of times that you might not have assumed something will work out or not. And then the C is the countermeasures. So this is very simple, but it's very powerful. So I think we're going to just do this as an example now. So I'm just going to write this for, and then if I'm writing too small, you at least roughly know what I'm writing here. So do people want to vote? Let's vote on a problem that we should do this for. It's fun to do it for things that are hard. You know what? I think let's start with the microplastics, because lots of you have thought about it, whether consciously or unconsciously. Right. So just background, most of you have been in the ocean, right? Yes, no? How many of you have taken in some water when you go to the ocean? Most likely you've been eating. If any of you eat fish, anything that comes from the ocean, we're all ingesting, inhaling microplastics to begin with. Just to get the sense of the scale of the problem, we know how much plastic we make, right? From production, you can estimate the set of numbers. We can go back and do the by the numbers for this. So the first thing you should do if you're about to start on a problem is to first tackle the by the numbers. So by this time, I would have assumed that if you're going to tackle something like this, you have calculated all possible aspects. You know the total global production of plastics, you know some of the sources, and you would find in the microplastic by the numbers that 95% or more of plastic is missing. So that's why this problem is so exciting. It's like the black or dark matter of matter. It's the real dark matter. We don't know where 95% of the plastic actually is. And what that means is because if you were to just go currently, if you measure and what you find versus the amount of stuff that you're putting, that doesn't add up. And one of the problems for that is undersampling. So when we go to the ocean is a volumetric space, right? It's the largest biosphere, maybe 90% or more of the volumetric space on this planet, even including the atmosphere, that is livable, is in the ocean. So we're talking about a massive volume. And when things go, like, for example, the last Tara expedition went out and they have just shown that the Mediterranean is the most polluted ocean. With 6 years of sampling all across, going back and forth, but only surface sampling. So one of the challenges that's associated with this as a problem is that microplastic doesn't just live on the surface of the ocean. Then just some numbers, and by the numbers, you would also write down, what is the scale? How do we define? Do people know? What's the definition of a microplastic? It would be important to put a number to it, because when we say the word, plastic bottle is not a microplastic. Do we know what that number might be? Yeah.
Less than 5 million liters.
So then it's basically effectively, let's say, nanometers, because there is nanoplastic as well. There is microplastic, but just for some kinds of arguments, just to say 1 micron to 5 millimeters. And some of this also just boils down to that this is the scale that's really hard to collect back. As of today, we think a lot about this problem in general. I am not aware of any scalable tools that can actually collect microplastics in the kind of dilution it exists on the planet to begin with. It's a massive problem. If any of you crack it, that is a phenomenal achievement. So this is also for just anybody listening in the class. We will talk about measurement, because I know Nima very specifically pointed out about measurement. But of course, beyond measurement, you also have to potentially remove it when you find that it's too much of it's there. Currently, I don't know any scalable solution. Okay, so you now have some numbers and things in place. So what would you think about? And then just shout out as you think, what could be the potential functional requirements for a technology that measures microplastics in the oceans? So what do you want to write in this column? And again, the trick that we're trying to take is take a very large problem and break it into pieces that can be handled. So what could be the potential functional requirements we might want to write down? Folks, if they have ideas, Henry, go ahead.
Sorry, my camera's off. You have to be able to collect the microplastics somehow.
So the functional requirement first is that you have to collect, or maybe I would generalize it, that you first have to be able to see it, because you might not be able to collect and then measure. Your measurement device could actually be in the ocean to begin with, but you have to be able to detect it, right? So that's an important functional requirement. If you're going to measure something, you have to detect it. So detect microplastic, and immediately you see, by putting this requirement, this was not an idea, it was a requirement. I can imagine 100 different ways of detecting plastic. So this is really where ideas come in. And now for just this one functional requirement, there is a fork in the road, right? So I could have many different methodologies that we will evaluate. Each one of them will have their own analysis, their own references, their own risks, their own countermeasures, and the cycle continues. And this is just literally one of your functional requirements. So I like that a lot, Henry. We will pause for a second on the ideas phase. I just want to finish all the other functional requirements. So let's just go and suggest any other functional requirements. Wani, go ahead.
Professor, what I had in mind was something that can survive in the ocean. as in the turbulence and all of that.
Yeah, I think
And
that's a
be
pretty important requirement. But then we're also making a little bit of an assumption there that this will be an in situ technology. And so that's okay, but we can write that as a functional requirement that it's in situ because there might be other means. Imagine, I mean, I'm just making this up now, but this is also the whole point of imagining. Imagine that microplastics as a function of time, because of all the weathering, emit a very specific volatile compound. And you measure it out in the atmosphere and not in the ocean itself. I mean, I don't know of one of that compound, it would be pretty dilute, the numbers are not that high. So I think in situ is probably the best way of thinking about it. But it is valuable to just realize that immediately you have made some kind of an assumption and you write that down. Because when you are going back to the sheet over and over again, you will have to think about it. So I'm going to write that in situ and I'll write survive in ocean. And survive is not a quantitative word because what does that mean, survive? So in the design parameters, we will put numbers here, like survive for a month, survive for a year, not release microplastic itself. Yes, what was your name again?
Lucas,
Lucas, go ahead.
I think it probably should have some like spatial or temporal resolution, so you can.
Yes. And so I think
Differences.
in the detect microplastic, what we could do is we will list the many ways that we do it. And every one of them will have a specific spatial and temporal resolution. And actually, it's very interesting that the spatial resolution maps what we care about here. Because if you built a machine that doesn't see a 1 micron particle, you're going to say it doesn't exist, right? So I like that here. And what we will do is that this will become, and you can see this is starting to get a little bit messy that it might not be. Do you know, Hope, if there is a sharper markers? So that I don't know whether they, yeah, this is not.
I can go find one.
Um,
Sounds pretty good.
yeah, let's use something actually. You guys know if these markers release microplastics? Is all of this microplastic? Our shoes, our cars, you drive every day. Where does the tire actually go? I had to replace my tire just last week. Where did it go? We are breathing it. It's all landing into the atmosphere and the ocean. So it's not a trivial problem. And we literally, yes.
What are they measuring the process? Because that goes to
Nobody does.
okay.
There's no test. You can't go to the doctor and say, hey, could you measure the amount of plastic content? There does not exist a test. Even knowing what the biological phenotypes or outcomes of plastic in our body are unknown. So there are some experiments, you make mice eat plastic and other stuff, but that's, very little is known. And so I think, this is one of the other aspects of let me just write this out. This is fantastic. Spatial, temporal resolution. And I think the one important thing I just want to have, I forgot to say this, but before I say, this design process, I know I'm talking about a pretty depressing topic, but it has to be fun. If you're thinking and you just don't feel all of these sets of things that you're thinking about should really light you up, that's the problem that you should work on. And so although you're working on a tough problem that may not have a solution, will feel hard at this early stage to even begin with, there's really no motivation. When we get something working, there is a lot of motivation. And so kind of one thing about this that I remember, another acronym that Alex always used to tell me, and I always like repeating it, is we're going to deal with fundamentals, but you can see already there is a word fun in fundamentals, and then there is the mentals. So do the mentals, but have some fun. So in that process, you can come up with crazy ideas. So in this kind of an idea phase, you can really fly because the analysis, references, and risks will bring you down back to earth. So some of these things you could put down here might be wild. And of course, if you don't do that, you will just not be able to explore the entire design space. And so just remember these two parts. This is important. I see Suraj's hand and I see Pawan. Suraj, go ahead. Did you have another functional requirement?
Yeah,
Go
one
ahead.
function. Yeah, hi. One functional requirement I was thinking was scale of sampling. Like you would need a large scale way of sampling the, the data. So
Yeah,
that
so I think the scale that you're referring is to the amount of volume of water. Is that correct? Because the
yeah,
ocean is
yeah.
big, and so volume, and this is a little bit different from the functional requirement for spatial temporal resolution,
Yeah.
because this is what you see, but how much water do you actually process through per unit time? Okay, I see another hand, and what was your name? How do you say that? ANRU. Okay, that's a new name for me. Yes, okay.
I guess going off like the microplastics, I imagine the ocean there are also like, other things that are the similar size, so like differentiating between.
Yeah. So in that scenario, in the functional requirements, I'm just gonna underline, when you say detect microplastic, only detect microplastic. And there is immense life, which makes us alive essentially. So half of the oxygen that we breathe come from microorganisms in the ocean. They all are in that same range, and they should not trigger. So one important way of saying that is, in any detection technology, you can say what is called the specificity and sensitivity. And this can be thought about, and we will talk about this when we do sets of numbers, is the false positives and the false negatives. So to a certain extent, this is a balance, because you could make an incredibly sensitive microplastic detector, but then it might start firing on other things that it's not microplastic. Or you could make it extremely specific, but then there's lots of times it might miss it, right? So what you're referring to is that in these sets of numbers on spatial temporal, it goes beyond that. It's not just spatial temporal. I need to know the sensitivity specificity of this detector, and it connects right here. You can intuitively think about, if I'm going to try making something very, very specific, it might be slow, right? Because I'm really trying to make sure 100% that I never trigger a false positive. And that might imply you to do more analysis. Like, we will talk about this. For example, we could think of mass spec, we could think of imaging, and some of those technologies, you could literally be doing molecular analysis of that piece of plastic, but that means for every one of them, that would take a long time. So there would be a hit. So an important aspect of functional requirements is they are not independent, right? How could they be? Because the product itself is a map of constraints, and different constraints push and pull. Because, so somebody didn't say cost, I'll say cost, because this is frugal science. I want this type of a detector to be deployed at every coastline. So do you guys roughly know how many people live on this planet? Maybe let's say 5-10 miles from the ocean. What's the population? Yeah.
Over 1 billion.
Yeah, so 60% or so of people. It's insane to think about. Like, our planet has, and many times, many people don't actually even visit the ocean or interact with the ocean, but they're close by. So you can think about the capacity of a socially citizens monitoring system like that the people are there. Where does most microplastic come from? And this is an important functional requirement. Anybody wants to say, do we know the major source of microplastics? Neon. Oh, Owen, go ahead.
I thought car tires create the largest source, but
So that's good, one source, but I'm just wondering, how does it enter the ocean? And you would have done this by the numbers, because how does it enter? Does anybody know?
Through rivers, water.
Rivers, all the rivers. That's the key. So one of the things that you could also think about is, oh, wait a second. Where do I want this technology to operate? As a functional requirement, do I want it out in the open ocean? Or is it better to be thinking about, because the macroplastic enters through there, but in that same process, it's also starting to convert into microplastic. And so the abundance of cities and close by cities is a massive source and aggregation of microplastic. So I could include something around here of the scale of the network that I want. And in that process, I could say, oh, I want the technology to operate at every major city in the world, right? So how would we put that as a functional requirement? Some of it is cost, but you also want it to be networked, right? So I could think a little bit about that. I want this technology to not be in isolation. And you can already see we're asking a lot already, but it's important to think about because we're trying to just reflect what are we sensitive to, what do we actually care about in this process. Okay, anybody else? I see Dia's hand and then Renal. Anything else that comes in functional requirement? And then I'm going to jump to design parameters.
I actually just had a question.
Yes.
You mentioned that like we could possibly use like molecular testing to like characterize each microplastic that this device finds, but it would take a lot of time. So
Yeah.
I was just wondering like where do we draw the lines like in general between trade-offs? Like you could use a less sensitive technique which takes a shorter amount of time, but it may not always be that accurate. So like where do you draw that line?
Yeah, so I think the line will be drawn very naturally as you proceed in this analysis. And what you would see that one set of technology, one set of ideas, one set of approaches meets your functional requirements and others don't. So when we convert these functional requirements into design parameters, we will put some numbers. So from a network point of view, I might say, you know, time is an important functional requirement too. You know, do you want this in 10 years? Probably not, because 10 years is too long a time. I mean, we're polluting our oceans now. You might say, I want to bring in something online as quickly as possible. And so I might put a time on this, which is like 1 year. I really want something functional fast, which means the stuff that works should get higher priority. And that might also require you to increase or decrease the set of resources that you might be interested in putting. So to answer your question, one important thing that will happen is as we start putting numbers on design parameters, when you start coming up with ideas, some things will meet those requirements and some won't. And then we have another way of writing on a pro and con list, which is called the pug chart. And that's where we will do these trade-offs. So we will write, out of this will emerge many ideas. We will make a cross sheet of ideas 1, 2, 3, and then we will do our criteria and see whether they meet the key functional criteria that we have discussed. And then you will see that you will have a way to shoot down a lot of things. So the purpose of FRDPARRC is when you start big, cover up the space, because you're going to be investing. I mean, for any project, it would be crazy that you could accomplish something with real problems in less than a year. It takes time. So when you're making an investment, you know, as a joke is, if you board the wrong train and you run backwards in the corridor, it doesn't help. So make sure you board the right train. So this is what we're trying to figure out, what train to board on. Because you might get excited about something purely for, say, oh, mass spec is so cool. It can actually see molecular signatures, but you're on the wrong train because the cost doesn't scale and it is not something that can actually be scaled up from a field perspective. It's great for testing out in the lab. And so you want to make sure that you caught that early on, because you would be investing a lot of time in. And again, all of these things, it's perfectly okay to keep going back and forth. So every week from now, as you're starting to think about, we're going to choose one set of a problem. I want everybody to do a FRDPARRC independently, but then you'll start sharing them, and slowly these FRDPARRCs will eventually evolve into the projects that you're thinking about. You can share them, let people poke holes in it, but this will evolve almost every week the more you understand. Okay, so let's jump to the next column. Mrinal, were you going to make a comment?
Yeah, I was thinking if you want to understand the level of microplastics in the ocean, couldn't we just sample the fish and check the tissues?
Oh, I love that idea. So it's like a meta sampling system and a biological approach. And now, so what's very interesting is how do we fit it in a functional requirement framework? Because it is an idea. So one way I could think about what you just said, Mrinal, is it's a little bit like this in situ. I could think about a biotic and an abiotic. You know, there might be a specific reason that you don't want a biotic solution, because maybe our understanding of the conversion rate of plastic in the ocean to what accumulates in fish is not known because it's a fish behavior. A very specific fish will decide what they eat, and we could get biased. So you might say, oh, I don't want that. Or you could say, no, I have understood and studied this particular fish so well that it is a very powerful approach, and I do want to use it. So in a functional requirement, you could say that your approach is biotic or abiotic. And in design parameters, you could write down explicitly what would be the constraints around it. And then the analysis then will involve, do we understand the conversion rate for native plastic in the ocean to the plastic that you found in a fish? But I mean, that's a brilliant idea. And this is exactly why you need to be flying in some sense when you're thinking about this, that it's perfectly okay to go in many directions. Yeah.
I was thinking.
And then can you remind me of your name? Irene. Yes.
So I was thinking exactly that, and I was thinking about how to test it, and I was thinking longevity of the fish.
Uh-huh.
I don't know if you could track them and you could see if they're not moving anymore. That means that they would have died in the ocean.
So now that is exactly in the design parameter. Now that's an idea. It follows in this biotic scenario. And then what you should do is, in this case, also do multiple versions of it.
You would have a standard curve, I would say. Like you would have maybe that same species of fish in a close environment and expose them to known concentrations of microplastics. So you could make a curve of like
So one of the nice things is you've already jumped to the next. The experiments that you need to do to prove and disprove these sets of ideas belong in the analysis. It also feels like analysis, like what you're describing. And so then here comes the experiment that you need to do to be able to say, do we have a concentration of plastic? So if this was the concentration in some molar per unit mass, molecules per unit kilogram of a fish, and there was some longevity in number of days, if there was a standard curve, that you would see that effectively higher sets of concentrations, the fish are not surviving, and so right there, and with lower sets of concentrations they have. So this is some kind of a curve. And then again, this belongs in the analysis. Yes.
It's like an extrapolation of that could also focus on like higher order, like higher the food chain intersection and stuff like that. You look at higher accumulation.
Yeah, and I think
extrapolate that out.
so that would belong in the biotic, but in the design parameter first. So you can see that every one of them has a massive expansion. And sometimes you might say, for right now, this is too much. Let me just blind this one. Like, let me not think about the biotic one for a second, because I just want to explore this design space. Because sometimes it does feel overwhelming. We just started with a problem, and it just keeps expanding and keep expanding and keep expanding. And so it's perfectly okay, but revisit it back again. When you feel like, oh, I've really explored this. Now let me just recover and then see whether these things will ever compare or not, which we'll be able to do in this pub chart. So I want to go back to design parameters. Do the simple stuff. This is a little hard. Yes.
Genova.
Yes.
So
In this design parameter, I'm making the assumption that we're not talking about measuring every single cubic meter of the ocean. So I think in the
Aha.
there has to be some like extrapolation based on
Yeah.
when we get,
Yeah.
we can assume the same with the rest of the ocean.
Yeah, I think that's a fantastic idea, in the sense that by the numbers, we should know the volume of the ocean. And then we need to ask ourselves, again, by the numbers, what is undersampling and oversampling? So sample size is a very important calculation that you would also do in that, to say, for certain sets of scenarios, and I think, this is statistically, you can write this down with the numbers that we know, and also put a margin of error to make sure that, I'm actually measuring order of magnitude more than what we know, because if there was hidden plastic that we were not detecting. The other thing people didn't bring up so far is where should we detect? I think when I had said the network, I was talking about coastlines. Problem with the plastic currently, and this is what we saw in Naples, we did a study in the Mediterranean at Station Napoli, where we were tagging plastics, and then we would watch them grow as a function of time. And what happens, and again, I'm just telling you the complications that throw a wrench in your plan. What we detected is that lots of microbial life grows on these plastic pieces. Plastic and major portions of plastics, you should also know what their buoyancy is, for example. So polystyrene, PPE, any one of those sets of things, you should have the buoyancy compared to seawater. Most plastics are actually buoyant. So they are lighter than seawater. But what was happening is that a microbial life grows on it. It makes it heavy. They sink to the bottom of the ocean. So if this is the water column, they sink to the bottom, and then there is very little light. The microbial life dies, and then the microplastic bounces back up again. And then it does that same cycle over and over again, which makes it super complicated. Where should I put my detector? And most of the time when people think about it, they say, I could say that a lot of this plastic was sedimenting down, which would be great. You could say, let's not do anything about the microplastic problem. Give it 100 years, it will all be at the bottom of the ocean. That's not true, because we chose plastics that we work with that are lighter. But then when we sample here, we sometimes don't find them. So I don't know if it was clear. Sorry, I'll just shift it. So what's happening is with the biological activity, and again, this is not even published. This is a group that we've been working with, Mariana and Station Napoli. What was beautiful there is that they have started to see this growth rate, and this growth rate that tells you how quickly it will sink. There is a dark zone because most of the things that grow in there up here can't grow down there. They all die, they'll come back. So one important aspect of this is also thinking a little bit about the volume, but the volume is a little tricky in this problem because it's not all volume is made equal. That's the challenge. That's what I'm trying to say. Not all volume in the ocean will give you the exact same numbers. So you have to do a depth metric. Maybe you need a measurement tool that actually can detect something across 4 kilometers. And then of course, in your design requirements, you can write that, but then eventually say that, okay, you know what? This is not a 5-year project. I need to get somewhere. And it's perfectly okay to say, okay, for right now, I know this is a problem. I acknowledge it, but I'm just going to work on the first 100 meters because I want to make sure that the scope of my project with the dollars that I might have and the urgency I need and the volume is still sufficient. And maybe I could model this. So this would then come into an analysis pipeline. I could potentially model this process mathematically and reevaluate based on the numbers that I found in the first 100 meters and convert that number into some other metric. Yes.
Oh, yeah, I was gonna say that even mathematics.
That's it. Yeah. And if people want for the class, if they want to choose some more simulation oriented projects too, it's actually quite fun. This is why this is important, right? You know, the idea that we started with is that for most design problems, unless you are really tackling them with the rigor, you miss the point. And so it's very important that although this feels really difficult, you could have a functional model for it, recalibrate that model, and then go back and put that in your detector. It's much easier to do than make a 4-kilometer plastic detector, which will have very low concentration at the bottom to even begin with, because there is certain rates associated with it. And again, I think this dilution problem is hard. Okay, so let's just jump to the next design parameter. I see lots of hands. So Nandkishore, we haven't heard from you, and then Suraj. And then could you just introduce yourself before you ask a question?
Hello, am I audible, Manu?
Yes, we can hear you.
Hi. Yeah, I'm a undergraduate student from IIT Kharagpur. It's my first time here, actually. It's been quite some time since I attended a live session. So,
go ahead.
Yeah, so I was thinking about the depth metric that you were talking about for the design as a design parameter, and
Yes.
I thought, like, why couldn't we try to go with the settling rates of the microplastics of different sizes, and then extrapolate it to estimate the concentrations at different depth levels, and get an idea of the concentrations at each level.
Yeah, no, I think that is true. One of the complication in this, which is again goes back to analysis because it feels like an experiment. Keep this in mind. This should feel like words. That's something that you can put right away. This will be ideas and numbers where you feel that you have put something quantitative by. This will feel like experiments. So now, Nandkishore, the comment that you made is very interesting. It turns out for different types of plastic, completely different microbial bacteria and life grows on. Their growth rates are different. And then because of that, the sedimentation rate is not something you can find from a catalog. I mean, here I could find the catalog sedimentation rate. I could say polystyrene, I know its density, and so hence I know it's sedimentation rate. But when life starts growing on it, we don't know the rate of the growth of all these microbes. And we're talking about tens of thousands of species. There are a couple of metagenomes now for microplastics that have been published. And they show that we have hundreds of bacteria. And a little silver lining in all of that is possibly they're using the plastic as the carbon source, which is another, we're not talking about mitigating the problem. And then another challenge, just so we remember, on the design parameter side, some amount of plastic will have a microbial coat on it. And so your detection now gets really tricky. So going back to sensitivity and specificity, and I'm not saying all, because we can do these measurements. So some of the experiments that they did there is that they would take plastic and they would put it in a fine mesh and hang it in the water, leave it for 1 month, 6 months, a year, and see the growth rate. And so then you have some amount of idea to what you're saying that could be put in the model. But again, all of that is analysis. And some of that is to prove a point where there might be a risk. I think accidentally I just mentioned a risk. I mentioned the risk that microbial life hides microplastic. And then you have to think about a countermeasure. Can anybody think of a countermeasure? If I give you a plastic that's coated with bacteria and algae, how would you detect it? So you have a piece of plastic, it kind of looks like this, but it is completely covered with algae. Suraj, do you want to mention, or was your comment about something else?
Yeah, both I can. I wanted to add a design parameter, which is like size exclusion, since we are looking at a particle of certain size. So size exclusion can be a design parameter here. And about the coating, like if we could stain it for DNA, then we could figure out how much biotic component is there in this.
So I think that's one that now you're not only looking at native, your instrument also stains things as it comes along to try to differentiate between biotic versus abiotic. Yes, and then yes.
I guess we're talking about countermeasures, and so
Yeah.
I was just thinking of like mass spec, right?
Yeah.
Like breaking things down.
Yeah.
Pieces.
Yeah.
So maybe we can have a countermeasure where I imagine the couch sheet isn't everywhere on the plastic. And we
Yeah.
can break it down. You know, like-
Yeah, and actually there's a very interesting countermeasure hidden in what you just said. And then I'll make a bigger point, which is I quoted it, but there could be areas where plastic signatures are there. And we do know these molecules are very specific. Plastics are not synthesized directly in biological life. So even a hint of it then does imply that there was plastic. So coverage is not 100%. So the countermeasure could be in your detection technology, even optically, because we will use, say, polarization microscopy or birefringence. Many plastics are birefringent. This is how you've seen those beautiful acrylic. Have you guys seen that? Maybe we'll take a little break to show you guys just one. Do you know if there is a browser here? Which one? There?
Here, that works.
Okay. So acrylic birefringence. And then how do I bring that up?
Oh, and then go to the right.
Oh,
And you would need to share the screen.
So this, for example, is if you put a polarizer, and I guess I'll do this for a fraction of a second. So you can all see that there are certain interesting optical features, and some of these features are specific to the kinds of plastics. And this is coming because polymers have orientation. And then remember from Benedict's class, we talked about how light interacts with matter. But we said that all elements have a common refractive index. But if by itself there is internal structure, light could interact with that structure and then scatter in different sets of ways. So you could actually pick that up. So there is a possibility of building specific plastics to be detected using, say, a technique like birefringence. I'm going to stop sharing. Henry, I think you had a comment.
Yeah, sorry. I think I was actually going to say if you shine a laser through it, how would that affect the laser? And
Yeah,
see
that's
if that.
similar. And what you are referring to is autofluorescence. So it turns out, did Benedict cover anything with fluorescence microscopy or no? Tiny bit? Yeah, I think it's this idea. And again, I think this is a common thing that will happen in the class where there is a hint of an idea and then it ends up being something that's so exciting to you, then you come and sit down and we'll spend a lot of time on it one-on-one or in teams. So depending on techniques, because the techniques people want to end up using or directions people go will change quite a lot. So autofluorescence is this idea that you can excite the molecules with a given wavelength, with a wavelength of light, and detect back. And from that, you can read out potentially what the composition is. Yes. And then what was your name again? Late. Like the late. In the machine shop, late. No. Did I say that right? Late.
Yeah.
Okay, yeah, that's how I know it. Yes.
Wondering for even if a plastic is entirely covered,
Yeah.
Is there no imaging that kind of goes through the material and then even if it's on one side and on the other is biological life, but if any.
Yeah, I think X-rays is one, and then again, you can write every possible thing here. So we can do X-ray, we can do fluorescence. So this is important. Now we're getting to the design parameters. Any other sets of, we could just do light microscopy, which is cheap and simple. There is a really fun paper that had come out, which they were looking at actually microwave signatures. So imaging, but using radio frequencies, because it's a dielectric. So I don't know how many of you did, you all did that calculation of capacitance. capacitance, two parallel plates, I want to measure the capacitance, and you put a given amount of dielectric in it. And it changes. Plastic is a dielectric, it's an insulator, so you could potentially electrically detect it. So that would be microwave. Any other ones? Of course, we have mentioned and tossed around mass spec, which breaks down the molecules into their molecular components, looks back, and then you can reconstruct what it might be. Yeah.
There's just a question for X-ray.
Yeah.
Is there anything like this make like X-ray? It's like usually it's like expensive and like you think about going to a doctor.
Yeah.
Is there a cheap X-ray alternative?
Aha, okay. You just triggered something in my head. I do this often much later in the class, but now I have to show it to you guys. So this is a complete diversion, but it's not my fault. This is Late's fault. Okay, so let me type. Actually, before I type anything, I need a material to show this to you all. No, basically it's a spot on which is everything in some.
Yeah.
Okay, so we're gonna expose Late to something. I have a scotch tape here, right? And you're gonna hear a sound. So I'll let you hear it too close. So you hear that? Yeah. So we just exposed Late to X-rays. It's not that much. It's kind of, I mean, you've been pulling scotch tape all the time. So so what just happened? What happens is some of you have heard this idea of triboelectricity. When you peel tape, there are two adhesives that are being peeled out, and nobody understands why. But we know, and we have experimental evidence that this produces X-rays. So I'm going to just do this for the class again. If all of you can see a piece of scotch tape, when you hear that sound, that produces X-rays. And, you know, for most time, we didn't even know this, but almost 10 years ago, a group, scotch tape X-ray, stumbled on this. This was first done by a Russian group, as a lot of things in the old days used to be done. It was rediscovered by an American group. And I don't want scotch tapes. I'll show you this picture. So literally, the mechanism remains unknown, but you can go back. There's an X-ray detector, and you can see at this little interface here. And what's happening is the X-ray is strong enough that you can actually take an X-ray. So that's somebody's finger. Oh, I'm going to just share my screen. Sorry. Share screen right there. And so again, you know, this is why I call this class Frugal Science, because the challenge of this is that suddenly an idea that you would never think is feasible becomes feasible in the context of, okay, Zoom, help me out here. Okay. So I assume you guys can all see this. You can do this in your kitchen. There is really not enough X-ray in there to cause any damage or something, but there is X-ray sources. And then what happened is effectively, there's a beautiful paper that you can read about it. I'll just do the Nature Scotch X-ray images. Sticky tapes generate X-rays, and okay, now I know what this is thinking. I meant Nature as in the journal Nature, not Nature. But you can see this here, and then you can go back, try reading this paper. Christmas could bring new hazards to unwrap your gifts. I don't think there is any hazard per se, but it is okay. How do I open this now? Oh, come on. All right. Okay. I think enough of a digression. You get my point. I think ideas are everywhere. So it turns out that there is a company that was started, some IP was filed, and they have been trying to build low-cost X-ray generators. Now, the problem is traditional X-ray generators require high voltage because you have to do this breakdown, you have to have these electrons jump from cathode to anode. And then in this scenario, it's happening mechanically. So they literally took two Scotch tapes and a motor that was going back and forth, and it was generating X-rays. And they showed that you can actually make an X-ray source. And then we have a project with a radiologist who I will bring up at some point of time, and we're looking at TB imaging and trying to come up with a mechanical way to generate X-rays for TB that require no electricity. So because the plates can be developed, they don't require any electricity. So you could really do a screening in the middle of nowhere, but require this mechanical device to generate enough X-rays. And they showed that you just generate a little bit of vacuum. So you take this, you put this inside a little vacuum with a bike pump, you can reduce the amount of air in it, generate X-rays. And, I don't, the application that this company was working on was really around airport securities and other stuff. I don't think it worked out in the end. But it would be fabulous if somebody wants to think about it, re-engage, and then especially in the context of TB, it's very useful. And I think, this is really why this is hard. It's this collision of what we believe is possible and what we don't know. So when we are creating this sheet, we are biased. We already believe. I was not going to write X-ray until you brought that up, because we just take it for granted that, oh, this is not going to be cost effective. And this is why you need to fly. You really need to just imagine. And often enough in that process, you might stumble upon something that then also may be applied totally somewhere else. And this is also the word science in all of this, because nobody has yet actually understand how this piece of tape makes X-ray. And often enough, this will be the kind of, I'll just draw something here. There are different kinds of technologies. So I think you can all see this. Okay, what did I just do? With a fully working. Now, let's try it out. Did I just flip it? Oh, yes. Okay. We've been talking about cost performance all throughout. Cost, performance. A lot of times, there are lots of established technologies that have a curve that kind of looks like this. High cost, flat performance, and then suddenly if you want more, you pay a ton more. So this is traditionally, this is when people have looked at technologies over many periods of eras and times, this is something that looks like. There are times and scenarios where suddenly you come up with another approach to the problem. The cost was significantly lower, had a performance, but then when you wanted more out of it, it really skyrocketed. And so there are sets of trade-offs that, oh, if I'm operating at this performance, this technology was actually better as compared to this, because, as you demand more performance, a solution that was okay at that performance might not be. But then there is another class of technologies. So these are established technologies. These could be the bleeding edge of whatever you want. And then there is what is a massive jump when you come up with something like this Scotch tape that nobody has thought about, and they can belong into a curve that lies in a completely different place, because it has no relationship to what determined the cost previously to begin. There is absolutely no, because what was the issue here with the larger X-ray is I need high voltage, but I also want portability. High voltage and portability is hard. You need analog circuits that can take high currents. There is a bound there for what you can do. But suddenly, if you flip the problem and say, I don't need high voltage, the curve will not look at all like what looked before. And this is what I want you to explore. As you are thinking about sets of projects, this is the curve. Sometimes these curves arise from consumer electronics, just because somebody is just making so much of something that they've really shattered that. Sometimes it just arrives from a fun idea. Sometimes it arrives from going back to history. Like in the 1960s, there was a Russian journal that explicitly talked about this, and it just sat there and nobody did anything about it until 2008. Somebody repeated it, added more explanations to it, and then suddenly it became a big deal. Now IP was being filed. So there's a lot of ideas just sitting there. And this is another thing that you all have to understand and think about, is go dig in literature when you're thinking about these ideas. Okay, so we're gonna quickly finish, because I have to finish a little bit earlier today. So we go back, sorry for the digression. The design parameters would be something that you would put explicit numbers on. So in volume per unit time, I should say something like a liter per minute. That would be pretty awesome. If that doesn't feel like, oh, the ocean is too big, then it says, no, I want 10 liters per minute. Whatever that is, you should write that down. And all of these are not being made up. They're coming from by the numbers. So now you can see why I was emphasizing so much, because otherwise this will feel like, oh, it's in vacuum, and you will take the wrong train. Does that make sense? Does it make sense? How does by the number reflect here? It doesn't tell you exactly what to do, but when you put something here, it can actually tell me. So say, for example, I mean, this is a beautiful analogy that I've been thinking about microplastics. It relates back to what Mrinal said. I've been thinking about sponges for a while. So in the biotic, instead of fish, I want to put sponges. First of all, they don't swim away, so they sit there. But sponges have massive pumps. So I don't know if you guys have all seen this. These beautiful diving images, and some of you who go diving or snorkeling have seen it. Sponges are massive pumps. And okay, I'm confused, left or right? Okay, so sponges, fluorescence. So images. So a series of sponge in a bay essentially filter water. Okay, there. So if you ever, some of you can watch these videos, and then let me try sharing this picture for a second. So sponges generate a massive amount of flow. They sit there, they take water in, it passes through the cells and it emits out. And one of the nice things about something like this is it happens at a scale of the bay. So sponges. Clearly it's, so this is fun. Okay, I hope it's gonna play. Okay. Come on. Okay, why don't we just do it as preview? So do you see he's injecting right there? And then massive, all of that is being pumped out. And this is continuous, nonstop, day in and day out, they're pumping. And so again, it kind of tells you, going back to volume, you can go back and do this calculation and say, for the amount of energy that a sponge takes, how much volume it's actually processing as a function of time. Yes?
So are they actually absorbing the microplastics?
They're absorbing both nobody knows, nobody has done that calculation. They are absorbing food. They're absorbing algae, and they're very specific to what they pick. So you would have to do this study to confirm. I think I've just been thinking about this because there is a saying that in all of oceanography, people say this, that if you have sponges in your bay, every day the bay is being cleaned by the sponges. And it is true. A lot of chemicals are being extracted out. And then again, this is really why this type of a framework is good. So if we just undo the screen share.
Yeah.
Pawan, you have a question.
Yeah, so in my lab in NCBS with Shannon, we had a postdoc who was working on this exact problem, and she was working on microplastics with Anchika, the Dr. Anchika. So she's working on sponges and she's finding microplastics in these. She does the mass spec and Raman spectroscopy to actually does it, and she sees them in the sponges, and she does it in many parts of coastal India. And so so I don't know if the papers are out, but they do study sponges for this exact purpose.
That is fantastic. Could you please post any of the papers or anything that's publicly known? And if it's not publicly known, then you don't need to post it.
I'm looking if the paper came out. Let me check, but I'll post whatever I find. Yeah.
Yeah, sounds good. So, and I think this is also one of the important aspects of doing this with the community is the fact that lots of people who are thinking about it should share sets of ideas. Okay, so I think I'm just going to finish this now. Design parameters are where you put the absolute numbers and your ideas. Now, analysis, as we already discussed for this, for every one of them, I need to know, for example, what are the signatures? If it's X-ray, I need to know the X-ray signature. For example, with X-ray, you can tell cartilage from bone, all kinds of different tissues from the contrast. Could you do that for plastics? Does every plastic have a very specific X-ray absorption index that you could use to be able to detect it? So in this, you would actually make that map for different types of plastics. You would have the numbers and say whether they are differentiable enough. Similarly, for light microscopy, you could say shape. Shape is a pretty interesting criteria. It's very easy to get, and we will show you now next week. No, not next week, Thursday, we'll show you a technology that we've been working on, which is a flow-through imaging system that allows you to tell shapes, and you get a whole bunch of shapes. And it turns out nature doesn't make these types of jagged edges. And so by shape alone, it's quite likely that you can actually detect microplastics. And that's what we do in kind of the pointoscope, for example. Microwave, there's a beautiful paper that has signatures. So you would put that in here and you would write the references. Say, for example, any reference that you find, it doesn't have to be the reference for that exact same application, but it has to be a reference for what you're basing your idea on. So somebody might have done microwave signatures of plastics because they were making capacitors. You take that idea and you put that in as a reference. Oh, I'm going to use now that framework to essentially apply. Because if everybody has done all this, then what's the point? Then the problem must be solved. So clearly that's missing, but the reference is to just make sure that you have a footing. So when somebody questions you, you're able to answer questions. Okay, and then I think risks and countermeasures we already talked about. Primarily every idea that you have, you should think of a couple of risks. Some of them may be just like, oh, I don't think it's high target, or in some sense, it might not be too critical, but it's useful to still write down. If something doesn't have a risk, that it might mean that you haven't thought hard enough about it. And then the countermeasures are just ways around it that you could still, and then if it turns out you can't find a countermeasure, that becomes challenging then to take that approach. So we're gonna wrap here today, but one important thing that I wanna mention is this is assignment number 2. So you've already done by the numbers. If you chose a problem to do the by the numbers, you can now do a FRDPARRC for that specific problem. You can also choose a completely different problem. You can also start thinking about, we've created a channel in Discord that's called Design Board or Ideas Board. That's where you can start writing and sharing, oh, this is a problem that I'm interested in. So write in detail the biodiversity problem, and then you can start doing the FRDPARRC. But you can talk to friends, work in teams, but everybody must make one unique FRDPARRC. So it's something that you should do by yourself. And this does take time if it's thoughtful. I mean, you can fill this up randomly and then those numbers won't guide you. It's not for me or anybody or for an exam. This is really going to be the ticket to the right train. And so you have to be thoughtful, you have to be editing it all the time. I like making large sheets. We can print and I can send you a PDF of this template. You guys can make PDFs, share them around each other. But we're going to try to create homework number 2, FRDPARRC, and people should share this. And then with it, you can also attach another sheet in which you are doodling ideas. So you can, right here, it's very hard to represent. You can represent ideas graphically. So that could be the doodle of say, oh, I have this X-ray detector, I have plastics coming here, I have a pump, this is how. So people have a visual sense of what you might be thinking about. Does that make sense? Yeah? Okay, I think for folks who came late, I had already said this is the most important class. So if you can practice this skill over and over again, you will realize that you can crack a lot of problems. And so I think the important part of this is just make sure that you're actually honestly practicing the skill and pushing yourself. If it feels easy, then you're scratching the surface or you haven't explored enough. And then it's perfectly okay to be out of your depth very quickly, because every one of these approaches require you to read 5-10 papers, come back again, ask questions, talk to us, just have conversation. And if you do this properly, I'll sit down with you and we'll walk through your FRDPARRC and we'll kind of go into details that potentially will lead to projects and projects ideas. The only important thing to remember, do a FRDPARRC for a problem that you actually care about. So you will all find problems that you care about. Okay? Any last questions? Yes.
If we change the problem from our original by the numbers, do you want us to resubmit by the numbers?
No, I think it's just for you now, but it's useful if you're going to start to do some numbers for it. And if you are so passionate about it, you will do a very extensive by the numbers. Again, that's the ticket to the right train. And especially if you're thinking about that as your project. Like this is a project class. So what really matters is what we end up doing and creating that didn't exist before. That's what matters. So it's a choice, but I would say that for practice purposes, if you're just choosing another problem for practice, do a rough estimate, get a sense for how big the problem is. Quick sets of Google to find some key numbers. And you might be writing here and say, oh, I don't actually know. And you go back to by the numbers. I think that's a much better strategy. Yeah.
What do you want to start by?
Maybe 1 week. When do you guys want to do it? You guys decide. 1 week is a good time. Maybe next Tuesday. Yeah. Okay. All right. We're going to call it a day. I have to unfortunately run, so I'm rushing a little bit. Otherwise, we would have spent a little more time trying to talk through this, but I think I'm going to do this in a couple of different ways. I usually like doing the open mic at the very end of the class, but I have a student that's giving a talk. It's already started, so it's an important talk, so I need to rush in. So we'll catch up, use Discord, and then I'm also starting to see some of you, I'm starting to remember name, and this is becoming the coherent group that's going to stick out. So that's exciting, finally. Lots of people get excited about this class, they come in and then they disappear. So, which is okay, but now look around the screen, these are the people to stay. And then in terms of teams, it will become important that you're choosing people in team that actually care about this class or are committed to go through, because it's no fun to create a 6-people team and you can't find people, right? So just, this is a contact sport. This is not an observation sport. So just make sure that you see people that you're choosing and recruiting to the team. Ask them directly, do you have time for it? Because they can all watch videos later. And this is very relevant. At this point, I want to make sure that people that are committing are actually spending time. Okay, and I'll see you on Thursday. Bye, everyone.
Bye.
Bye-bye.